It is an honor to introduce our first plenary speaker of the week, Dr. Sid Redner. Sid, as I'm sure many of you know, has really done a tremendous amount of work contributing to first passage time theory, extreme event theory. So it's great to have him here this week. I hope we all have a chance to chat with him. He was at BU for a very long time. Now he's been at the Santa Fe Institute doing plenty of really wonderful research. And so today we'll hear him talk about dynamics of foraging and starvation. Thanks.
Thank you, everybody, and I hope you'll applaud at the end rather than at the beginning. So the work I'm going to tell you about today is in wonderful collaboration with a number of colleagues over a long period of time: Olivier Benichou, Uta Bhatt, Marie Choupeau, Paul Krupski, and John Rodler. So the question I want to ask, the basic question, is if you imagine a forager wandering around an environment and trying to eat resources, how long can this forager live? And it turns out that this is a very standard problem in ecology. And the classic work is based on the notion that there are rational foragers who have perfect knowledge of the environment and so make rational decisions on what they want to do about this tension between exploration and exploitation. However, we are going to talk, so this leads you to like optimal foraging strategies. And I guess MacArthur, Pianka, Charnoff, classic work from the 70s on the subject. What I'm going to be doing is the opposite case of completely ignorant foragers who have no environmental knowledge. What kind of strategy should they adopt? Well, they don't have a strategy, but what will they do, or how long will they live, given their ignorance and lack of knowledge of the environment itself? So let us try and make a model for this ignorant forager. And so here's my forager, a little bunny rabbit, very cute. And this bunny rabbit has no brains, and it just wanders around randomly. When it hits a piece of grass, it eats it. And if it comes onto a bare spot of land, it doesn't eat and gets a little bit hungrier. And so as it's wandering around, when it's not eating anything, it's gradually starving. And so this makes the model the starving random walk model. So let me be a little bit more precise about what I call the starving random walk. So here is a lattice in 2 dimensions. Each one of these little green dots is a little morsel of food. And here is my forager somewhere in the middle. And to be specific, there's one parameter in the model, which is the stomach capacity. So let's call S. It's going to be a basic parameter throughout the talk, the stomach capacity. And for the purposes of this illustration, let's suppose that the stomach capacity is 6. That means that I can walk 6 steps. And if I don't eat within 6 steps, I die. And so we'll see what happens to this forager. And so in this case, we're starting at t equals 0. And the bunny rabbit has just eaten the morsel of food in the middle. So he's got a time of 6 time steps left in the rest of his life. And so let's set this guy walking around. And so every time he moves, if he eats, his lifetime is reset to 6. And if he's wandering around in a desert with no food, so here he's reset to 6, but now he's wandering around in the desert. He's wandering. He's running out of time. He should turn right, but he dies. So this is the basic model. We want to understand the dynamics of this model. So here's the outline of my talk. I'll first discuss this basic starving random walk model and describe the dependence of the lifetime on the spatial dimension and on the stomach capacity. Those are the 2 basic parameters in the model. And then I'll talk about a number of biologically or ecologically motivated extensions of this basic model. One is you might be a little bit greedy, so that if you see food, like you're a graduate student, you see pizza, like, on the floor below, you can smell it a mile away. And the question is greed good or bad? If you're clueless and you walk on food and miss it, does that help you or hurt you? And then if you're a bit frugal, like you say, well, I'm on a diet, I'm not going to eat today because whatever. And so does that help you, your lifetime? And finally, does it help to be intelligent or not? And finally, some parting thoughts. So let's first of all talk about the case of one dimension where one can solve everything in complete detail, but let me give you a heuristic understanding of the lifetime of starving random walk in one dimension. So here is our bunny rabbit, and it's in an interval of size 2. And so when the next step, it's going to step either to the left or to the right. If it steps to the right, now the interval length is of length 3. And so every time it steps, it's going to gradually increase the length of the interval. And so maybe it continues hitting on this side of the interval, but then it jumps over to this side of the interval. So it's a length 5. And the crucial point here is that there comes a point where the length of the interval hits a critical value, which turns to be square root of 3 times the stomach capacity. And the point is that at this point, if I were to diffuse across to the other side, the time of it would take would be exactly s. And so at that point, the far side is irrelevant. So there's actually 2 stages in the lifetime of a starving random walk in one dimension. There's this initial carve-out time, and then there's a time in the semi-infinite interval. And so when the far side is unreachable, we can forget about it. And then so the time to carve out the critical length desert, so the time is just L squared over 2, and so that's 3/2 S. So there's a first stage, you live a time of 3/2 your stomach lifetime of just carving out a interval such that the far side is unreachable. And now the next part of this process is we have to study the problem of a semi-infinite desert. And this turns out to be a very pleasant first passage exercise, because we want to ask, if we forget about the other side of the desert, how long do I take before I return to the origin? And so that return probability is just the integral of the first passage probability up to your stomach lifetime. And so that's a simple integral. It's error function complement. It has its asymptotic behavior. And given this return probability, we can compute the number of returns just as a geometric sum of k, the number of returns, times r to the k, 1 minus r, summed over all k. This goes like s to the 1/2. And then the average lifetime while you're doing these returns and always coming back to food is just the first moment of this return time distribution. And that scales like s to the 1/2. And so putting this all together, the total lifetime of your starving random walk is the time to carve out the critical length desert, which we computed in the previous slide, and then times the number of returns times the average time for each return. And then there's the last component where if you wander and never come back, you live s steps. And so the sum of these things, if you add it all up, you get 7/2 s. So that is the heuristic argument for the lifetime of my starving random walk. Now, the thing is, you can do this kosher, and so here's the kosher calculation. I'm not going to say anything except just to flash the slide, just to say that you can do everything entirely, precisely, and then you get the correct answer, 3.267 ... f. So this heuristic argument was not bad at all. And so one can ask now that we've solved the problem in one dimension, what happens in higher dimensions? Because, not too many foragers live in one dimension. And so here's simulation results for 1D and 2D. And this is actually not a solved problem at the moment. What is the lifetime of the starving random walk in 2 dimensions? Here on a double log plot, it looks like it's scaling like s to the power alpha, where alpha is around 1.9, which kind of smells like maybe s squared over log s or something like that. But this is still an open problem. And the other thing that makes the 2-dimensional problem hard is that if you just look at typical traces of where the forager has been, so this is just 3 random samples of the starving random walk. So here, this guy had a lifetime of about 10,000, and you see it goes in a range of about from 70 to -10, -60 to 0. Here, this guy had a lifetime of 300,000. This guy had a lifetime of 400,000. The crucial point here is that you need to know, like, how long can you go before you visit a brand new site that you've never visited before? So this is related to visitation statistics in a very subtle way. And the point here is that we don't understand this desert geometry, and we don't understand the scaling exponent in a precise way. So that's an open problem. In higher dimensions, things become easier because, as you can imagine, as the dimension becomes high, the true environment and the average environment get closer and closer to each other. And if we plot now the logarithm of the lifetime as a function of the stomach capacity, and this is on a semi-log plot, so that suggests that the lifetime scales as exponential of s to some power omega. And it turns out that a reasonable fit for this omega is like d minus 1 over d, which is a natural hypothesis that there's some dimension-dependent behavior which will go to simple exponential in the limit of infinite dimensions. And this also is something that we think we understand, but not in complete detail. So this is also still semi-open, and I think ripe room for mathematicians to maybe prove something. One thing that we can do is the mean field approximation, which is that if you assume that visitation statistics are governed by a Poisson process, so in very high dimension, you have a certain one probability of hitting a previously visited site and starving or getting more hungry, or visiting a new site and then getting completely full again. And so if I just assume in the mean field that it's a Poisson process, so lambda is the probability that a random walk hits a previously visited site. So lambda is the probability that you go hungry today and move one step closer to death. And so one can draw a very simple phase diagram, or like, I don't know what to call it, just a diagram of like the state of the system. If you've just eaten, you're S steps away from starvation. Every time you visit a previously visited site, you move one step closer to starvation. But if you come to a site with food, then you go all the way back to being full again. And so we have this very simple state space for what is the state of my starving random walk. And one can write down very simply a recursion formula or backward Kolmogorov equation for the time to starve starting from a given site. So the probability lambda, you move one step to the left and you're getting one step closer to starvation. And with the probability 1 minus lambda, you're fully sated. And so that corresponds to one step. With probability lambda, you move one step closer to starvation. With the probability 1 minus lambda, you go back to the fully eaten state, and you've spent a time 1 in doing either of those two possibilities. And so this is the backward Kolmogorov equation for this hitting time. And for the T1, it's slightly different because you've hit the point right away. And so this is a very simple recursion formula that you can solve. And if you solve it, you end up with the lifetime being exponential e to the minus s log lambda. So at least in infinite dimension, it appears that it's exponential growth. So that's the basic starving random walk model. And what I want to now turn to is some simple extensions of this model that have all kinds of interesting behavior. So first question, what is the role of greed? So what I mean by greed, which is that, think about like, a graduate student at the, before the colloquium, and, the cookies are put out and they grab all the cookies. Whereas like, I'm an old guy and like, if I look at food, I gain weight. So I try to stay away from the food. So the thing is that maybe, is greed good? Greed is good because you might say, well, I consume resources as they're encountered. And so I prevent myself from starving. And we know that in all kinds of computer science applications, the greedy algorithm is often considered the right way of doing things. On the other hand, why greed might be bad is that if you're very greedy, you enlarge the desert around you where there's no food anymore, and so you have to wander further and further. And so maybe it's better to not be so greedy and make the desert so big. So what is the right answer? And well, let's see what the answer is. So in the framework of our little bunny rabbit, our starving random walk. So if the random walker is far away from food, then with equal probability he hops to the right or hops to the left. But if my starving random walker is close to food, then with a probability p, which is much bigger than 1/2, he or she will go to the food, and with probability 1 minus p, hops to the right. So this is the basic model, very short range greediness, only nearest neighbor greediness. So there's a basic parameter here, the greed parameter, which when p is equal to 1/2, there's no greed. When p is equal to 1, then greed is 1. And notice, though, that it seems natural that, well, p should be bigger than 1/2, but keep in mind that we could have p less than 1/2, which correspond to negative greed. We'll see something funny happening with that momentarily. So let's look at some simulation results for the lifetime as a function of the greed parameter. And again, because when we first were thinking about this, we never even thought about negative greed. We won't worry about this side of the plot for a little while. And so I'm plotting the lifetime for a starving random walker with stomach capacity S, and I'm dividing by S so the data fits on a single plot. So you see that for S equals 10, greed is good. As you get more greedy, your lifetime goes up. So it seems very natural. When the stomach capacity is 40, greed is still good, but it doesn't seem so good at the very beginning. It's like it's not increasing very much. And here comes the first surprise, is that when stomach capacity is really huge, greed initially is bad until finally when greed is really strong, then it becomes good. So there's something bad going on over here. And so that's first point, non-monotonic. And for 640, it gets, this minimum gets even smaller. So there's this weird feature that if you're really greedy, it's actually bad because you tend to carve out a very large desert. And then in this large desert, you're more likely to starve. So let's try and compute and understand this apparently non-monotonic behavior. And so, excuse me. So there's 3 steps in doing this calculation. One is, again, we have to compute the time that it takes to build a critical length desert where we can forget about the other side. Then we have to compute the lifetime in the semi-infinite desert, and then we add these 2 things up to get the total forager lifetime. So first thing we need to do is understand the first passage properties of a random walk in a finite interval, but with perturbed hopping probabilities at either end. So here we hop to the left with probability P, probability Q to the right. At this side, I hop with the probability P to the left, Q to the right. Everywhere else, it's half-half probability. So this is a very nice first passage exercise. Compute the first passage properties of this slightly perturbed, boundary perturbed random walk. And so this is all standard stuff, so I'm not going to go through every detail, but the thing is that we can write down the equation for the exit probability. And so like for the exit probability from site N, half the time you go here and you have the exit probability at site N plus 1, half the time you go this way, you have the exit probability from site N minus 1. But the boundary equations are slightly different. And so when you do that, you can solve it and you get like some expression for the exit probability that when P is equal to 1/2 just reduces to just the good old linear profile. But for P not equal to 1/2, there is some weird little perturbation right at the boundary. Similarly, for the unconditional exit time, you have the same kinds of backward Kolmogorov equations, and you can solve them, and you get the result for no perturbation, and then a term which involves 2P minus 1, so it goes away when P is equal to 1/2, but there's some perturbation. And then one can also compute the conditional exit time, so let me call U, which is E times Tn minus. So Tn minus, the probability starting at site N, hitting the negative side. So that's what I'm writing the backward equation for. And again, it's just turning the crank and you get some expression. And so from this, we get 2 basic results. One is what I call TL minus 1 minus, which is the probability of starting at L minus 1 and going all the way to the other side. And it goes like 2/3 L squared, which would be the result for a good old random walk, but with another perturbative term, 4/3 L over P. And so if P is very small, this can dominate this guy and it changes everything. And then there's another term here, T1, which is the probability of starting at, say, at site 1 and either hitting this side or that side. This is linear in, there's a typo here. There should be an L in front here. I don't know how that disappeared. So 1 minus PL and then times this constant term. So now using those facts, we can figure out the time to build the critical length desert. So here is my T1 and here's the L now restored. And so if it takes a time, basically L to build to hit a boundary, a distance L away, then to build a interval of length L, I have to add 1 plus 2 plus 3 all the way up to L. And so the time to build an interval of length LC, which I don't know what it is yet, is just I sum this up and I just get 1 minus P L squared over 2. And now to compute the length of this critical size desert, this crossing time, which at the critical length desert, which we still don't know yet, but we can compute it by setting this crossing time equal to the stomach capacity. So this is, you just get to the other side of the desert just as you're about to starve to death. And so from this, one can compute the length of this critical size desert, and it has 2 different limiting behaviors depending on whether P is much bigger than 1 over root S or P less than 1 over root S. And so this is the source of all the fun and games here because there's these 2 different limiting behaviors. So now that I've found the length of the critical size desert, I can compute the time that it takes to build the critical size desert because I just take the build time and plug in my critical length size, and I get, again, 2 different answers depending on whether P is much bigger than 1 over root S or less than 1 over root S. And then when P is of the order of root S, these 2 things are of the same order. They're basically the same. So once we have that, then we need the lifetime in the semi-infinite system. But in the semi-infinite system, most of the time you're wandering around, and every once in a while you come back to that like edge of your semi-infinite system. And it turns out that, again, that's like the same kind of reasoning as before. It's just that the semi-infinite time is more or less the same as what happened in the case of no greed, but there's a small perturbation here, but it's not going to affect anything. That's why I didn't go through all the details of this semi-horrible calculation. So now we put this all together and we add it all up to get the forager lifetime in one dimension. And so we have our build time times our semi-infinite time. And again, it depends on whether p is much bigger than 1 over root s or much less than 1 over root s. And if you stare at these things, you'll see that when p is of the order of 1 over root s, there's different terms of different orders of magnitude, but they come same order of magnitude and of the order of s to the 3 halves. So let me tell you the consequences of this. First of all, if you plug in p equals 1/2, so that would be for this formula, and you just work it all out, you'll find that the time is 5/2 s plus a term which changes sign when p goes through 1/2. So this shows you that the lifetime actually has a change in slope at 1/2, and so it's a transition from monotonic to non-monotonic behavior when, at least in this theory, s is bigger than pi. Whereas we saw in the simulation, s had to be of the order of 160. So this argument has got, needs some refinement to make it really quantitative. But the more interesting feature is that when p is of order 1 over root s, if you plug in here 1 over root s, you'll see a term of the order of s to the 3 halves, and then s to the 1 and s to the 1. So the s to the 3 halves wins out. So there's a huge maximum at p equals 1 over root s. So the point here is that if you're someone who's always on a diet, and saying when you see food in front of you, you step away from it. Well, when your stomach capacity is large enough, that turns out to be an optimum strategy for survival. And so if we go back to our plot, and now let's extend it for negative greed, then what happens here is this behavior. And so the main point here is that this lifetime, somehow I went backwards I don't know how I did that. Yeah, so the point here is that this peak is scaling this peak, which is growing here, is growing as s to the power 3 halves, and the location of the peak is at 1 over root s. So if you plot the peak value, you'll see this 3 halves behavior in the location 1 over root s. So it's really rather queer behavior. So we can ask what happens in 2 dimensions, which is perhaps more realistic. And here we have very little in the way of theory, but we have some simulation results and some arguments like why greed in 2 dimensions should also be kind of ambiguous. So what happens when a forager is very greedy in 2 dimensions? So let's think of a sort of typical trajectory of a greedy forager. So this guy's doing a random walk, he's walking around, and he comes to this point in the trajectory where the way in front of him has been blocked because I've already eaten over here. And since I'm greedy, there's food over here, there's food over here. And so I have a choice. I can either go up or I can go down. And it's going to happen equally likely. But so suppose I choose going down. And you can see right away what will happen. Well, if I'm really greedy, I just carve out all the food in this desert. And at the end of the process, I'm in the middle of a large desert, which has a large radius. In this case, it's not very large, but you can see I can generalize this argument to make a larger desert. And at this point, I have no food in my environment. And so I've got to somehow cross over all this desert in order to find food. And so I would argue that starvation is likely. So here is the behavior of the lifetime, and again, scaled by s, so it all fits in the same curve for different values of s. And you see that when your stomach capacity is not very large, actually, you should be greedy. So graduate students being greedy for the food at the colloquia, that makes perfect sense because they don't have a lot of money or not a lot of stomach. So they've got to eat whenever food is available. But if you're a big fat cat, which hopefully I'm not going to become, but maybe I am, I don't have to be so greedy to survive. So here the answer is greed good or is greed bad? The answer is it depends. Another thing which we looked at, which we found very amusing and very cute, was does it pay to be clueless? And the thing is that if you're searching, like if you're a golfer, you all know who's a golfer here. I don't know, but if you drive a ball into the rough, the grass is deep, and you're looking, and where the heck is the ball? And it's right there, and you just never see it. So here we're doing a forager who only eats food with probability epsilon when he sees it, he or she sees it. So here is a picture of the state of the system. Here's my forager, this little blue dot over here. And here, this is a line full of food. And let's see what happens as a function of time if my forager is clueless. So as the forager goes along, sometimes when it hits food, it eats it and it makes a little desert. But here, all during this trajectory, it's walking in the grass and saying, I don't want to eat any grass, I'm full. And so eventually, as you go throughout, as a function of time, you'll see that you carve out deserts, but you also, inside of the deserts, you carve out local oases. And in these local oases, well, that's food that can save you down the road if you're very hungry. So this feature of like carving out this combination of deserts and oases is something that makes it helpful to be clueless sometimes. And so here is a simulation result. I mean, these numbers are kind of ridiculous, but nevertheless, the main point is just to show that for a forager who can live 1,000 days or 1,000 time units without food, that there's a well-defined maximum of the lifetime as a function of this cluelessness probability. So here, roughly speaking, 10 to the minus 2 probability of eating food, and your stomach lifetime of 1,000, you have this well-defined maximum in the lifetime of the forager. Okay. Next one is frugality. Yes.
So is it clear that that's unimodal? Like,
yeah.
Okay.
Yeah, I mean, so here I'm not presenting any of the calculation because it's a bit more hairy, but yes, it appears to be unimodal, but I have to say we've only focused attention on one dimension where we can do the calculation. Another natural possibility is, does it pay to be frugal? And so what that means is that, you think about like a lion who is just like brought down a wildebeest. And so the lions are having this feast, they're eating, they're gorging, they're lying in the sun after having their meal. And another wildebeest walks by and they go, oh God, I can't eat another bite. So the point is that lions have this feature that they gorge themselves, and then for the next couple of days, they don't bother hunting anymore, and then they get hungry again. And so the question is, you should only eat when you're sufficiently depleted. So here's the sort of model, is that you have your stomach. Here's the stomach capacity, S, a fill level. If you're below this fill level, you eat. If you're above this fill level, you don't bother eating. So this is also like the problem of like if driving on a highway, when the gas tank is like getting close to empty, and the next gas station is 20 miles away and the next one is 40 miles away, should you wait for the 40-mile away because it's cheaper, or should you do the 20-mile away? So there's some interesting optimization questions to ask here. And so let me show you, again, simulation data of the behavior of the lifetime as a function of this fill level compared to the overall stomach capacity. So down here, this means that you wait until the needle's almost bouncing on empty before you decide to fill up. So here you're maximally frugal, where here it's like as soon as you eat, then you've got to eat it again like 5 minutes later. And then it turns out that as a function of the stomach capacity, there is again a well-defined single maximum of the lifetime as a function of this frugality parameter. Okay. So the other point, though, is that notice where the position of the maximum is, that as your stomach capacity gets bigger, you have sort of more resources to keep waiting. And so the bigger your stomach capacity is, the more frugal you ought to be. Okay, so the last topic I want to present here is, does it pay to be smart? And this one was, this is actually quite recent. And so here, imagine you have a blob of food, and let's imagine that you have a dumb forager. And so a dumb forager is a dumb forager. What I mean by dumb forager is that it has a limited brain capacity, and so its detection radius for food is small. So you can naturally think that, a big part of like your metabolic output is based on like, driving your brain. And the bigger your brain is, the more it costs you in metabolic energy. But the bigger your brain is, the further away you can detect food. So let's imagine that a dumb forager is one whose detection radius is relatively small. Now let's look at what happens for a typical trajectory of a dumb forager. So the dumb forager is doing a random walk, and you see that because it's dumb, it steps very lightly because it doesn't require a lot of metabolic energy. When it finally hits the detection radius, it goes zoop, right to the food. On the other hand, if you have a smart a smarter forager. So, sorry, one more thing to state here is that because the forager has not much brain capacity, and the brain capacity is playing a role in the overall metabolic rate, then each step here is metabolically cheap. So you can see the steps are very light. But now if you have a much smarter forager, it has a much bigger detection radius. And if it starts at the same point as the dumb forager, well, it's much bigger because it has a bigger brain capacity. So each of the steps requires more energy, but then when it gets to the detection radius, it goes directly to the food. So here, each step is metabolically expensive. And the fundamental assumption in all of this is that the metabolic rate of your forager is some basal metabolic rate B times plus a constant times the detection radius. So here there's sort of a fundamental parameter alpha, which says that, if your detection radius is R, that the overall metabolic rate is this basal metabolic rate B plus alpha times R. So either alpha or R are kind of measuring how much extra metabolic energy is required to run your system. So we want to ask, like, what is the which strategy is better? So the question is, what is the optimum intelligence to maximize the lifetime of the forager? And so here, here the calculations become rather hairy. So I want to try and give you a sense of how the calculations go without going through every single horrible detail of it. But the point is that there's sort of two natural possibilities that one can think about for the relationship between the distance between the forager and the food. So X is the distance between the forager and the food. R, in this particular case, is the detection radius of my forager. And V times S. So the point is that when I go within the detection radius, then I move at velocity V directly to the food. And so V times S, that's VT, that's a time. That's a distance that I'm going to go before I starve to death when I'm running towards the food. And so the point here is that when the detection radius, when VS is larger than the detection radius, it means that you just go directly to the food and you don't run out of energy in so doing. So that's basically what happens. On the other hand, if food is outside your detection range, so here is my forager, here's the food, here's the detection range, so that means I'm going to have to random walk for a while. But again, VS is the metabolic energy or the time that I can go without running out of food. And so if I get to this boundary with enough metabolic reserves left over, I'll get directly to the food. So when the food is outside of the detection range, what you do is a random walk. So you do a random walk, something like that. And finally, when you get right to the range of where the food is, then you go directly to the food. And as long as this distance is less than V times S, you have enough metabolic energy on board to actually get to the food. And so these are the two calculations, or the two situations I have to deal with to compute the lifetime of my forager. So here again, the two situations. And so, did this shut off?
I think so.
Did I do something?
No.
It's the battery.
I don't know. I can hear you fine, but I'm up
Okay.
front,
Yeah.
so
Should I just shout?
I think so.
Okay. Okay, so again, here were the two situations of just going directly to the food or random walking around and getting to the food. And we have to calculate the probability of these events and the time that it takes for each of these events. And so here, this tau sub b, tau ballistic, this is the probability that if I have Poisson distributed food, so this is a Poisson distribution, and this is the time that it takes to go directly, X divided by V is the time that it takes this is the average time that it takes for a forager that's within the detection range to go directly to the food. On the other side, if I have to diffuse first I have to compute the hitting probability. What is the probability that I successfully get from this point to the food without starving to death? So I have to say, well, when I have to compute the first passage probability starting over here, and I have to ensure that the amount of food that I have left available is my stomach capacity minus the metabolic energy I'm going to burn up and running towards the food when it's within the detection range. So this is just an error function complement, and these little tildes here mean that this is x minus r, and s tilde is s minus r over v. And once I have this hitting probability, then I can compute the sort of time of this trajectory, which is a combination of the diffusive part and the convective part. And so this is the convective part. This is the diffusive part, which is the first moment of the first passage probability up to this time s tilde. And finally, the eating probability, the total probability that I either eat going by direct route or by this route and not starving to death, is just I have to ensure that if I'm within a distance r, then I go directly. And if I'm outside a distance r, I have to ensure that it actually hit. And then I have to average over all possible lengths, distances between the searcher and the food. And so we get this quantity Q, which is the eating probability, and there's two pieces to it. There's the ballistic part and the diffusive part. And again, the calculations get more horrible, so I'm just trying to give you a sense of the overall feeling of the calculation. The average first passage time is then the number of ballistic, this is the number of ballistic segments. I guess I should have this thing, number of ballistic segments times the time for each ballistic segment, and then times the number of diffusive segments. And here I'm assuming that ballistic and diffusive segments are uncorrelated with each other. And then there is finally the, there is, sorry, I forgot to just mention, and then there's this last piece S, which is the part where you're wandering the desert and starve to death without eating. So you have to add that to the lifetime. So now we can ask, so what does all this give you? And so here we actually plugged in numbers we actually use from real biology, is that we tried to take numbers for like a typical 1.1 kilogram mass animal and a 1 kilogram mass animal, and length of steps 50 meters versus 0.2 kilometers. And the point here is that one has a very well-defined maximum for the lifetime of the forager as a function of this detection range, which is in some sense a fundamental parameter of the model. And so it's not, I don't think it's necessary, one shouldn't take the numbers very seriously, but the main point here is that there is this well-defined maximum of the lifetime as a function of the detection range. And this strange peak, or this cusp, this is happening because as you increase the detection range, the metabolic cost gets so large that essentially the forager transitions from being what I would call effective. An effective forager is one who, when it gets within the detection range, it has enough onboard energy to reach the food, versus a feeble forager that by the time it reaches the detection range, it doesn't have enough food to even run to the food without starving to death. So maybe this is not quite a realistic limit, but it just shows that there still is nevertheless a well-defined maximum. And then we can also do the same thing in 2 and 3 dimensions. And so here, again, you know, it's like this maximum was robust no matter how we played around with the parameters. And so this is showing for different values of alpha, which is that coefficient of the metabolic rate as a function of the detection radius, either 0.1 or 0.5. Yes.
In multiple dimensions, if you see multiple sources of food, do you go to the closest one, or do you choose one at random? Or
Thank you for the question. So in the case of in the case of multiple sources of food, again, if I only have like a limited detection range, I just wander around until somewhere I'm within a detection range of whatever food is, whatever food I happen to come to, and then I just go to that one.
So I guess set a measure 0 to exactly encounter 2.
yeah, I guess because they don't.
Yeah. Oh, I guess it's discrete.
Okay, so I'm at the end, and so let me just end with some final comments. So first of all, I hope I've given you a sense that the starving random walk model is very simple. It's very cool, and it has a lot of rich phenomenology. And I think we've only scratched the surface of the phenomenology. And there's also lots of variations on the starving random walk model because, you know, if I'm a lion who's just eaten a wildebeest, and so I eat and I'm full and I'm whatever, then why is it that I have to like always eat to complete satiation every single time? So if I have like just eaten last night, and I see like a little bit of leftovers and I take a little bite of it, why do I like gorge myself? So, I mean, the starving random walk model has this notion that you're always gorging yourself, which is maybe not the most realistic model. But the main point here is that we found the dependence of the lifetime on dimension and S. One dimension we understand completely, infinite dimension we understand, intermediate dimensions we sort of understand, but I think that for people who are more rigorous than I am, I think there's lots of fodder to play with. So I'd say we've partly solved this problem. Is greed good or bad? And so the answer is, it depends. Is it good to be clueless? And so clueless means that you eat with probability epsilon whenever you encounter food. And once again, the answer is yes, it's good to be clueless. But again, the more clueless you are, the bigger your stomach ought to be. Is it good to be frugal? And the answer again is yes. So maybe that's a good lesson for life. And is it good to be smart? I like to think it should be good to be smart. Just don't be too smart. Let me just mention a few other things that I didn't discuss here. One is that obviously if resources can replenish, then you can imagine that if the replenishment is more than the consumption, that you will live forever. And in fact, we can compute a immortality transition as a function of the replenishment rate. Another thing which is really open, and I'm inviting anybody to talk to me about it, is what happens if you have multiple foragers. And so people, you know, two people are competing for the same resources. And, you know, if I carve out my desert and then some poor schlep behind me is like wandering through the desert and I'm at the edge of the desert, you know, gorging myself on cheesecake, and someone else in the desert is screwed. Like what's, you know, what is the nature of the competition with multiple foragers? So that's really an open problem. So if you don't mind, I think this is perhaps the right audience to do shameless advertising. So please excuse the next slide, which is that there's a book that I wrote 25 years ago. And now there's a second look at the same book that's going to appear in early 2027. And so highlights many new chapters, many expanded chapters. You can read this for yourself. The text, the table of contents and the preface of the book are both posted on my website. And the crucial point here is that it's 70% more content. So the first book was actually rather light and thin. This one you can now use as a paperweight. Thanks for your attention.
So, Sid, very fun problem. This reminds me of almost of the problem of a random walk within a random walk. Do you know about this?
So this is you have a random walk trajectory, and then you launch another random walk within the random walk.
Within that, yeah. It seems a little bit like that, except okay, the shape of the random walk is kind of expanding, right, over time. Yeah. Like, do you know if?
I mean, this strikes me as this kind of problem that Greg Lawler has probably worked on. Somebody like that. I mean, you know, I vaguely remember some papers like 35 years ago on this subject, random walk within random walk, but
it feels like there might be a connection. Like,
yeah, I don't know what more to say except that wow, it sounds kind of cool.
Okay.
Yes.
Yeah, just a point of clarification. The large S limit. So when you choose to eat, when you hit a site, you fill up completely.
Right.
Is that so? You don't incrementally
correct
fill up.
Yeah,
even in your large S limit,
that's right. So you imagine that the environment is so like replete with food that no matter how big your stomach is, you can eat to your fill.
Okay, but if the S is very large, would you be?
Yeah. So I mean, this incremental model, as far as I know, has been only very partially explored, and so that's also a really good point.
And then your frugal in the large S limit, is that 1/E? That optimal?
I don't know.
You know,
Yeah, yeah,
you have them in the large S's, go to 1/E, which is the standard,
like the secretary problem.
yeah,
kind of thing.
yeah, or whatever they want to call
Good observation. I have no
Exactly.
idea.
Okay.
Let's talk. Yes.
So, like real environments probably are more patchy than this like very dense environment that you start with, and that potentially bears upon how greedy a forager might want to be, I guess, if an environment's quite sparse. If once I find food, well, I better eat it all because I don't know when I'm going to find it again.
Right.
Can you do the first passage time calculation in that case?
So I would say that like until I would talk about the intelligent forager, I was assuming that the lattice was completely full of food.
Yeah.
But in the case of the intelligent forager, we had to actually have the food like Poisson distributed. So
Right.
It sort of swept under the rug because it becomes a much more detailed. But yes, we can do the calculation for food, which is Poisson distributed rather than uniformly distributed. But I did not check about like the role of greed or whatever on that. So that's an interesting aspect that, you know, it's an exercise, but it's certainly a doable exercise.
Cool. Thanks.
So I know that Olivia Benichou did some work on adding intermittency into the motion.
Yes.
Which helps cover more ground. It seems to be a theme running through the analysis. Of course, it makes everything a lot more
Right.
complicated, but
So you're asking just like what happens if you have like not Brownian diffusion, but some other transport mode.
yeah. And then switching back and forth maybe between.
Yeah.
the two.
Well, you know, I mean, you know, Olivia and I are collaborators on this project, and we have a very different perspective because I like to live in the world of just pure diffusion. He loves intermittency and you know, Hurst exponents all over the place. My feeling about all of this is that all it does is it changes quantitative details. It doesn't provide like some new phenomenology. So I would say that, yes, he's also looked at intermittency on some of these, you know, starving random walk problems. And to my perspective, it only changes quantitative details. So, you know, it's like, I could take it or leave it, but he would get very excited about it. And he would yell at me that, you know, you're missing out. So. James.
I really like the last point on the competition. So before the shameless advertising. And I think the reason why I liked it was because I was thinking about it all the way through how audiences would change, but also just like from a personal perspective, you know, having finished the PhD, coming into the world of work, I am greedy. I want the money. And I do wonder, like, I don't know, do you think about like the economic kind of applications there? Like, I don't know, is there room for like a statistical physics manifesto on surviving in a competitive economy?
Well, all I can say is that in the case of the competition, let me sort of reveal something else about this that I think is very cool, which is that there's a classic problem in the theory of random walks, the number of distinct sites visited. But now suppose you have two random walkers, and on each lattice site is a gold coin, and you send these two random walkers going. And if you come to a site with a coin, you collect it. If there's no coin there, you don't collect it. So there's a competition between the different, you know, between the two random walkers. And you can ask like, who's going to win and who's going to, you know, what is the probability distribution of your winnings? And then in the context of the starving random walk, it's like instead of collecting coins, you're collecting food. And so at some point you don't collect enough food, you just die. So this whole notion of competition enfolded in with this visitation statistics, I think is actually very brand new and very open and in progress. And we can discuss as you want.
Yeah, perfect.
Yes.
Other questions for Sid?
What is the so I know that in the model there are kind of different things. What's the functional difference between greed and frugality, and why are they not part of the same effect?
Well, I mean, at least in the framework of parameters of the model, you know, the greed was very simple in the sense that if there's no food around you, you're just a pure starving random walk. You don't notice anything. You just random walk randomly. It's only when you're at the boundary and, you know, like I see a plate of cookies here and, you know, I got to get it right away. So the frugality was just that even if the plate of cookies is right there beside me, I can choose whether to eat it or not eat it. So there are different sides of the same kind of coin of like being sort of self-centered, I would say. But yeah, that's the best I can say.
Also, what does it mean to have negative greed, like physically?
So negative greed meant that when you come to food, you say, boy, if I don't move away from it, I'm going to eat it. So you move away from it. That's what negative greed meant.
Can I ask, have you done some preliminary work on this replenishing of resources? And if so, like how are you setting up these?
Yeah, so no, we actually have done some work on it. There's a paper with Olivier and Marie and myself on exactly this and this phase transition. But again, I think that we did like the simplest model and the most unrealistic setting. It was just we made the model so that we could solve it. But
It was the idea that like if there's a site you've been to before, there's just some probability that there's food there again.
yeah, so the thing is that with this, the thing is that there's actually two possibilities. One, can you say there's Poisson replenishment, or the other one is that there's a refractory period before this get replenished. If you're thinking like, eating grass in the plain and then it takes 6 months for the grass to reappear. And these cases are actually quite different from each other.
Right. They produce qualitatively different results.
Yes, exactly.
So the idea there is that in one case you have time dynamics of the replenishing, and the other one it's
Right, no
sort of
memory.
stationary.
Exactly, yes.
Okay, great. Let's thanks it again. Thank you.